see the next example in special cases. We have already solved two examples for special cases. Today we will see the third example. Okay students, now this is the third example wherein we are going to apply the special case. Now the first step that we do is usual, that is find out whether the truss is stable. After that we will find out the support reactions. We can see that the number of members that we have in this example is 7, whereas the number of joints I'm having is 5. Again, the support reactions will be 3 because I'm using a hinge support and a roller support. Hinge support having 2 reactions and a roller support having 1 reaction. So the total number of reactions being 3. I can see that my right hand side is 7, whereas my left hand side, that is number of members, is also 7. So I can call this as a perfect truss. So the next step that we do in solving a truss is finding out the support reactions. I have a vertical reaction at A for the hinge support and a horizontal reaction as well. For the roller support at D, I have only one reaction, that is the vertical reaction. Now, I'll first look at the horizontal forces that I'm having in this example. The horizontal force, that is the reaction force I'm having, is at joint A, that is HA. Now, if I look at this 5 kilonewton force, this is an inclined force which is acting towards joint A. Now, this force is acting exactly in the center of side BD of this triangle. So what happens is the angle that this force makes with the horizontal happens to be 30 degrees. So when I resolve this force, the horizontal component would be 5 cos 30 and the vertical component would be 5 sin 30. Now, since the answer that I'm getting for the horizontal reaction at A is positive, that means my assumption of the direction that I have assumed for the reaction at A is correct. So, I won't be changing the sign or the direction in that case. For the vertical reaction, I have two upward forces, that is the reaction forces VA and VD, whereas I have three downward forces, the 5 kilonewton force, this 5 kilonewton force, and the sine component of this force, that is 5 sine 30. So three downward forces, two upward reactions, that is VA and VD. Now, to find out the support reactions at VA and VD, what I can do is I can take moment about any one of the joints, that is joint A or joint D. So, if I take joint A, what happens in this case? There is this force, 5 kilonewton force, which is going to create a clockwise moment. So, for that, the force is acting downwards. So, 5 into the distance, the horizontal distance I need to find out. Now what happens in this case? Since this side is 10 and it is an equilateral triangle, this distance will be 5 meters. So 5 into 5, I'm taking the clockwise moment as negative. So negative 5 into 5. Now what happens about this 5 kilonewton force? This 5 kilonewton force is again going to create a clockwise moment. So that would be again a negative direction for me. So that would be minus 5 into the horizontal or the perpendicular distance over here. The perpendicular distance in this case would be 7.5 meters. Now, the vertical reaction at D is acting upwards, so that is going to create a anti-clockwise moment. So that would be a positive direction for me. So I'm taking it as Vd into 10. Now, what about this force, 5 kilonewton force? Why I'm not taking that force into consideration while taking the moment? The reason for that is, you'll know that whenever a force is passing through the moment center, that force is going to create a zero moment. So since this force is passing through the moment center, that is A, the moment of that force becomes zero. Now, when I solve this equation, I'm getting the vertical reaction at D as 6.25 kilonewtons, and my assumption that Vd acting upwards is correct because I'm getting the answer for Vd as positive. Now what I'll do is, I'll put the value of Vd in the equation of Fy, that is this equation. In that case, I'll get the value of Va as well. So even that is coming out as positive. So my assumption that Va acting upwards is correct. So this is how I have calculated these support reactions. Now the next step being, I have to find out the forces in all the members. So the next step that we need to do in this case is find out the forces in all the members. Now, by using method of joints, we need to find out the forces in all the members. But before that, we need to just check whether I can apply any special case in this case. In this example, I mean. So, joint C. Joint C, if I look at it, I have two collinear forces BC and CD. I'm having one more collinear force, that is AC, and the 5 kilonewton force. So do you think can I apply the special case over here? No. The reason for that is I have one more force, that is the force in member CE, and by special cases we know that I need only 4 forces at a joint. So I cannot apply special case at joint C. What if I move on to joint E? If I look at joint E, I can easily apply the special case over here because I have 4 forces and the forces are collinear, like force AE and ED are collinear, whereas CE and this 5 kilonewton force is collinear. So I can say by observation that force in member AE is same as force in member ED, and force in member CE is same as the 5 kilonewton force. I can directly write the force in member CE to be 5 kilonewton tensile. Force in member AE will be same as force in member ED. Now, what I'll do is I'll move on to the next joint, that is, suppose if I take joint D. What happens at joint D? I don't know the force in member ED. I don't know the force in member CD, but I know this vertical reaction. So in that case, I have only two unknowns, that is ED and CD. I can easily apply condition of equilibrium and find out forces in both the members. I have the 6.25 kilonewton force, that is the reaction force acting upwards. So I will show it in the upward direction only. I cannot take the force to be acting away. If I take that, then I have to show the negative sign for that as well. Now, the force in member CD is the inclined force. So what I need to do for that? I need to find out the angle. And here in this case, the angle is clearly given to me as 60 degrees. I can see that the force in member CD is coming out as negative, so it is a compressive force. I can put this value of CD in the equation for Fx equal to 0 and find out the force in member ED. The force in member ED is coming out as positive, so I can say that that is a tensile force. So coming back to my original figure, I have already calculated the force in member ED and the force in member CD. Now, the force in member ED, by observation we have said that at joint E, the force in member ED will be same as the force in member AE. So I can conclude that at this point itself that force in member AE is same as force in member ED. So this is how I have already calculated the force in member AE as well. Now, if I move on to joint A, what happens at joint A? I already know the force in the horizontal reaction, that is HA. I have already calculated the VA, that's vertical reaction. I have got the value for AE, but I don't know the force in member AC and the force in member AB. So I can apply condition of equilibrium over here. I have two unknowns, I have two equations. I can easily solve that and find out the support reaction. I mean the force in members, that is AC and AB. Now, what I need to do in this, I just need to find out the angles over here and apply condition of equilibrium. I already know the angles. The angle for AC is 30 degrees, whereas for AB is 60 degrees. Now, we will apply the condition of equilibrium over here. Now, I can write the equation for y direction as well. I've got two equations over here. Both the equations have two unknowns, that is force in member AB and force in member AC. What I can do is I can solve both the equations simultaneously and find out the forces in member AB as well as force in member AC. Now, both the values that I'm getting are negative. That means both the forces, that means the force in member AB and in AC are compressive forces. Coming back to the original question, I have calculated the force in member AB and AC. By observation, I can clearly say that the only force that is remaining is in member BC. So for that, I can take any joint, take it joint B or take joint C, and I can find the force in member BC. Now, just for to simplify this case, what happens over here is if I take joint C, at joint C I'm having extra forces like this force as well as this force, or you can say any of these forces, whereas at joint B I'm having only three forces, that is this 5 kilonewton force, force in AB and the BC force. So I can easily take this joint, solve it with less number of calculations and get the answer for force in member BC. We have got the force in member AB, and that force is a compressive force. So we have to just take care of that sign. When I'm resolving the forces, the angle I have is 60 degrees for both the forces. So we can see that the force in member BC is 2.89 kilonewton compressive force. So I have already calculated this force as well now. So the last step that I need to do is tabulate all the results. By observation, we had already calculated the force in member CE, that was 5 kilonewton. So what I'll do is, I'll just tabulate all the results now. The force that I have written first is AB. So I need to find out the force in member AB, then the AC force. Over here you can see that I have calculated for AB, that was 2.89, and for AC it was 7.48. Both are compressive. In this you can see that the force in member AE is 3.6 as well as in ED is 3.6. Both are tensile. BC. We have calculated BC to be as 2.89 kilonewtons compressive. CE is 5 kilonewtons and CD is 7.21 compressive. So this is how we have calculated the forces in all the members. Now I'll take one more example, and in that I'll show you the n number of zero forces that can be occurring in a given example. Thank you.